All right, so our goal is to prove the Cauchy integral theorem for triangular paths. But first let me remind you about all of our notation for this. So if I put angle brackets z1, z2 for some complex numbers z1 and z2, then that's going to be a path which is a line segment from z1 to z2. So it's defined like this. If I put angle brackets and then three things, z1, z2, z3, then that stands for a triangular path that goes, let's say here are z1, z2, and z3. It goes z1 to z2, then z2 to z3, then z3 to z1. And I can express that using the concatenation notation. It's taking these line segment paths and just concatenating them. To get the concatenation to work, you do have to parameter shift the domain. So this path runs from 0 times 0 to time 1, parameter 0 to parameter 1, as it's defined to. But this one needs to be shifted to run from 1 to 2, and this one needs to be shifted to run from 2 to 3. Then you can concatenate them like this. So when you see angle brackets z1, z2, z3, it's this triangular path starting and ending at z1. When you see delta, or triangle, of z1, z2, z3, then that stands for this set, which is the interior and boundary of the triangle with vertices z1, z2, and z3. All right. So with that notation in place, let's state the Cauchy integral theorem for triangular paths. Okay, let f be a function on an open set D, and I'm not assuming that D is a domain. I'm assuming f is analytic, and I'm only going to work in a certain triangle that's fully inside D. So even though I'm not assuming D is path connected, I basically am assuming that the region that I'm working in is at least path connected, in fact a triangle. So let z1, z2, z3 be not just any old points in D, but points such that the triangle they span is a subset of D. So that means not just the boundary of the triangle, but the interior has to fully be contained in D. Okay, then the Cauchy integral theorem states that the contour integral of f, our analytic function, on this triangle path is 0. Okay, so this is theorem 2, 2, 5. Given an analytic function, a contour integral on a triangular path, as long as the function is defined and analytic on the entire triangle, including the inside of the triangle, the contour integral vanishes. So if we knew this about not just triangles, but if we knew this about any piecewise differentiable closed curve in the domain D, then from our previous results we can conclude that f has an antiderivative or a primitive in the domain D. But this is weaker. This is just about triangular. This is just about triangular paths where the triangle's inside is contained in D. So there's no way we can use this to get an antiderivative for f right now, at least no easy way at all, not even on the triangle, because our earlier result required that all contour integrals along loops vanish. All loops, not just triangular ones. Okay, but this is a step along the way, so you could call this the lemma that's needed for the more full version of the Cauchy integral theorem. The major hard work will be here, though. So this is where we'll directly use the fact that f is analytic. We will somehow have to use the definition of derivative or something like that. Okay, so let's get started with the proof. So here's our setup. And we want to prove that the contour integral along the triangular path, z1 to z2 to z3 back to z1, vanishes. So we will start by constructing a sequence of triangular paths. Let's call them alpha n. And each path, alpha n, is going to be a triangular path, so it'll be made out of, let's say, z1n, z2n, z3n as the vertices. And I'm just putting these parentheses around here to say this is a sequence indexed by n. And how will we define the sequence? Well, recursively. So I'll tell you what the zero position, the zeroth term of the sequence is, and then I'll tell you how to get the next term from the previous term. But it's going to be a little bit involved. So the zero position is not involved. That's just going to be our original triangular path on which we're trying to prove the contour integral of f vanishes. However, the recursion step is going to be a little bit involved. So, by the way, when I make this definition that alpha superscript 0 is this, I'm also sort of defining z I 0 to be z I, where I can be 1, 2, or 3. Okay, so the way in which I'm constructing the sequence of triangular paths is that I'm constructing the sequence of vertices. That's probably the correct way to think about it. We're constructing the sequence, 3 sequences of vertices simultaneously, recursively. And then the sequence of triangular paths is the sequence of paths that traverse those vertices. Okay, so how to determine, say, what is alpha 1 from alpha 0? So for alpha 1, we choose one of the following. So there are 4 little triangular paths that we're going to construct out of alpha 0. So let's make a picture to start with. I think this will be easier. So let's say z1, z2, z3 are like this. Then this path that I just have drawn, that is alpha 0, right? And what I'm going to do is look at the midpoint here, and the midpoint here, and consider a triangular path with these vertices. So, like that. So I'm kind of focusing on looking at the midpoints, cutting up the triangle into 4 subtriangles. So this path, this pink path, I will call this alpha 0 sub 1. This one here, I will call this alpha 0 sub 4. This one will be alpha, all right, I want to make this bigger actually. It's going to be worth keeping this up. Okay, so going around the outside, we have alpha 0. Then focus on these midpoints. Cut the triangle into 4 smaller triangles. Then, given alpha 0, we're going to focus on 4 possible choices for what alpha 1 should be. And the 4 choices are this one, which I'll call alpha 0, 1. This one, which I'll call alpha 0, 2. This one, which I'll call alpha 0, 3. And this one, which I'll call alpha 0, 4. So, what am I actually defining here? For example, I'm defining alpha 0, 1 to be the triangular path that starts at the midpoint between Z1 and Z3. Let me change this to Z2, and let me change this to Z3, so it matches my notation and the textbook's notation a little bit better. Although it doesn't really matter, but here's Z1 to Z2 to Z3. Then what's alpha 0 sub 1? That's going to be a triangular path starting at the midpoint between Z1 and Z2. Then it goes to Z2. Then it goes to the midpoint between Z2 and Z3. Alpha 0, 2 is going to be a similarly constructed sort of thing. So it's this one. It starts at the midpoint between Z2 and Z3. So same notation here, but a little 2 and 3 there. It goes to Z3. And then it goes to the midpoint between Z1 and Z3. So the same notation here, but with a 1 and 3 there. And you can imagine how the others are defined. Let me just write down alpha 0 sub 4. That one's in the middle. That one just looks a little bit different because it goes through 3 midpoints. So it goes from the midpoint of Z1 and Z2 to the midpoint of Z2 and Z3. To the midpoint of Z1 and Z3. Okay, and I've omitted actually writing out fully what are alpha 0, 2 and alpha 0, 3. Okay, so to recap, we start with one particular triangular path. The one on which we want to prove the contour integral is 0 for this theorem. Then, from it, we look at 4 possible smaller triangular paths, and we're going to name them by the same name of the first one, the one we started with, except with a subscript 1, 2, 3, or 4. So if there's no subscript, then it's the one we started with. And if I put a subscript 1, 2, 3, or 4, then it's one of these smaller pink paths. I'm going to choose one of these, and I'll tell you how we'll make the choice, to be alpha 1. And the idea is to continue by recursion. So if I'm trying to determine alpha n plus 1, and I know alpha n, then alpha n plus 1 is going to be one of these 4 choices. Alpha n1, alpha n2, alpha n3, or alpha n4. Where, what do I mean by these? I mean alpha n is going to be some triangular path going along the outside, so starting here and ending here, and then alpha n 1, 2, 3, or 4 are going to be these smaller triangular paths inside. Okay, so what I haven't told you is, for the recursion step, is which one do we choose? given alpha n, what should I let alpha n plus 1 be? Choose the one that maximizes the contour integral. So the recursion rule is we let alpha n plus 1 be let's see how to write this. Alpha n I, where I is one of the four choices, 1, 2, 3, or 4, such that the integral of the contour integral of f along alpha n I is maximized. Okay, so there are four choices. We choose of the four choices the one that makes the contour integral the biggest. Okay, so that's our recursion rule. Let me erase these actually not very useful definitions and leave the picture up. That's going to be a little bit more useful. By the way, when we define alpha n plus 1, we're also defining z1, z2, and z3 n plus 1. So that's how we're choosing these vertices. So each time these vertices are being chosen to be either a vertex from the previous triangular path or one of the midpoints, because we're setting these to be sort of one of these four possibilities. All right, so there's our recursive construction. Now, we need to prove some things about it. So the first thing to notice is a relationship between the contour integral of f along alpha n, the outside, and the contour integral of f along the little alpha n sub 1, sub 2, sub 3, sub 4. So maybe I'll start by summarizing what we have. Let me summarize a little bit. Alpha 0 is the starting one. The one where we want to prove the contour integral of f is 0. And alpha n plus 1 is the one of alpha n 1, 2, 3, or 4 that maximizes contour integral of f. All right. So now what we need is a relationship between the contour integral of f along alpha n and the contour integral of f along these four little ones. So this is, I think, a good way to see it. Let's draw a larger version of this diagram. And midpoint, midpoint, midpoint. And let's think about all of the let's think about the contour integral along each of the line segments here. So how many line segments are there total? There's this one, this one, this one, this one, this one, this one. So that's 6 pink ones on the outside. Let me orient them. Sorry, this is Z1. And actually, let's focus at the end position. So this is Z1, Z2, Z3 at the end position. So there's these 6 pink line segments. And let's see, green. Let's make 6 actually green line segments. These 2 on the inside, these 2, and these 2. Okay, so I've drawn 6 pink and 6 green segments, so it's a total of 12 line segments. And I want you to think about the contour integral of f along each one of these 12 line segments. So like this pink one, for example, that's the line segment Z1n to the midpoint, Z1n plus Z2n over 2. So that's a contour integral along that line segment, plus a whole bunch of pink ones, plus all of the green ones. And let's just say the last one in your list is one of the green ones. I don't have a very good way of ordering them, so this is not the clearest way to write it. So let me just write sum of contour integrals of f along each of the 12 line segments shown here. So this quantity, this complex number, is a sum of 12 terms. Contour integral plus contour integral plus contour integral, 12 of them. Now there are 2 ways to look at what this evaluates to. On the one hand, you can see that the green ones cancel, right? So in this sum, there are 6 green terms, and they cancel. The contour integral of f along here cancels with the contour integral of f along here. One is the negative of the other, because as we've seen, when you reverse a path, your contour integral just gains a minus sign. So one way to look at it is this sum of 12 terms, all the green ones cancel. And then you're left with just the pink ones. But the pink ones are just the contour integral of f along, actually along alpha n, right? The outside triangle. So that's one way to look at it. Another way to look at it, instead of canceling the green ones on the inside, is that this pink one, and this green one added together give you the contour integral of f along alpha and 1. These give you the contour integral of f along alpha and 4. And hopefully you're noticing that the arrows are oriented in the right way to match things up with our original definitions of alpha and 1, 2, 3, and 4. And then this one, that really does give us the contour integral of f along alpha and 2. And this pink one plus this pink one plus this green one gives us the contour integral of f along alpha n 3. Okay, so on the one hand, you can cancel all the green segments with each other and be left with only the pink segments, which is this. Or on the other hand, you can focus on each triangle and see that you have a sum of 3 segments that makes up alpha n, contour integral along alpha n 1 plus that, and that. Okay, so we have established that the contour integral of f along the outside equals the sum of the contour integrals of f along each of the sub-triangles. This will give us a certain inequality. Let me check that I actually turned on the sound. Okay. That got me paranoid for a second. Okay. Do I want to erase this yet? Yes, I think all we need is this fact, that the contour integral of f along the outside equals the sum of the contour integrals of f along the inside triangles. So that gets us that the contour integral of f along alpha n is bounded above by 4 times the contour integral of f along alpha n plus 1. Okay, so why is that? Well, okay, let's just think about it. If not, then what would happen? If not, then the contour integral of f along alpha n would be, well, it is this sum, so using the triangle inequality, it's less than or equal to the contour integral of f along alpha n 1 plus 2, 3, and then 4. But each of these is less than or equal to the maximum of the 4 of them, right? So, and the maximum of the 4 of them is how we define alpha n plus 1. So each of these is less than or equal to alpha n plus 1. Right, the contour integral along alpha n plus 1. I don't think I framed this in exactly the best way. I shouldn't say because if not, I should just say because. So I have this inequality because this is less than or equal to this by the triangle inequality, which is less than or equal to, and then I have a sum of 4 of the same thing. So I have here 4 that. So it's pretty direct there. All right, so the choice of alpha n plus 1 being the one of these 4 paths that maximizes, that chooses the maximum term among these 4, that ensures this inequality. Okay, so I think we don't need this anymore. We actually just wanted that inequality. Okay. So let's kind of summarize what we're doing in a picture, I guess. So we start with Z1, Z2, Z3, and we're looking at this triangular path. And then we take midpoints, we cut it up, and then we say, well, pick the subtriangle that maximizes the contour integral, and make that your next triangular path. So say it was alpha 0 sub 2, so maybe it was this one. Then this becomes my next triangle that I focus on. So then I split it up into midpoints, based on midpoints, into triangles like this. And then I say, well, to get alpha 3, pick the one of these that maximizes the contour integral. Maybe I get alpha 1 sub 1, so I end up picking this one. Then I split it up, and then I take the subtriangle that maximizes the contour integral. Maybe it's this one. Split that up, take the subtriangle that maximizes the contour integral, and so on and so on. And each time, the contour integral, at most, or at worst, you could say, gets multiplied by 4. So whatever was the contour integral at the beginning That's what I'm trying to show vanishes. That's the whole theorem. We're trying to show that original contour integral vanishes. Well, that is less than or equal to 4 times the contour integral here, which is less than or equal to 4 times the contour integral here, which is less than or equal to 4 times the contour integral here, and so on. So what do we have? We have what at first looks like a not so good bound. Sorry, 0, the original one, so this is the one that we're trying to show vanishes, it's bounded above by 4 to the n. So at worst you can only multiply 4 by 4 n times, and you have this. Okay, so remember we're trying to show this is 0, and there's kind of a good thing happening and a bad thing happening, with this bound at least. So if we're trying to show this is 0, then it's good that we're bounding it above by something times this, because these paths shrink in length. And we know that if you make a path shorter, then that is a way to decrease contour integral. Not saying it always happens, but it at least helps, right? So it's good that these paths are getting shorter and actually going to 0 in length, because you get smaller and smaller triangles. But on the other hand, it's bad that this is growing exponentially. So right now, it's not clear that we can show this is 0, but we will show that it's 0 by showing that this can be made arbitrarily small for a suitable choice of n. Now, remember what we haven't used at all yet, the fact that f is analytic. We haven't used that, and that's really important. Somewhere we're going to need that in order to guarantee that this shrinks fast enough. All right. So, okay, so we've got all these triangular paths that we called alpha n. Let's define the corresponding triangles, like the subsets of the complex plane that consist of not just the image of the path, but also the interior. So, with our current notation, with our current notation, we could do this. So this is a sequence of triangles in the plane, or two simplices, whatever you want to call them. And it is nested. So the 0th triangle contains the first triangle, contains the second triangle, and so on. So it's an infinite nested sequence of triangles, each one inside the previous one. All right, so there are two things that you have to believe so we can proceed. But you're also allowed to ask about these things on Campus Wire and try to get them down perfectly. So first, let's believe for the moment at least that triangles are compact sets. So this is a nested sequence of compact sets. And the second thing you have to believe is a feature of the completeness of the plane, is sometimes the way it's phrased, which is that if you have a nested sequence of non-empty compact sets, then there's a point that's in all of them. In other words, their intersection is non-empty. So hopefully it's maybe intuitively plausible that if I take a triangle and then cut on midpoints and take a subtriangle, choose one of the 4 subtriangles, and then cut on midpoints and choose one of the 4 subtriangles, and do that forever. Maybe it makes sense intuitively that there's going to be some particular point that I'm zooming in on. Of course, that's not rigorous, and one should prove these things, but let's just accept that so we can proceed. So the two things that I'm asking you to accept is these are compact sets. That's one. And two is, if you have a nested sequence of compact sets like this, all non-empty, then there's something in their intersection. So there's a gap because I'm asking you to accept these two facts. And then after the gap, we conclude that there is some point z0, let's call it, in the intersection of all the triangles. Okay, so let me erase a little bit. Let's keep this bound up here. So let me just write it like this. That bound will be needed. And since I'm going to erase and try to use this space, let me keep this fact about z0, that it's a point. It's a point that the triangles are sort of closing in on. Okay, now we're going to focus on the differentiability of f at this specific point, z0. Okay, so since f is differentiable at z0, there is some that's not a good way to put it. Let me just write it like this. We can say f of z equals f of z0 plus whatever is the derivative of f at z0 times z minus z0 plus some remainder function. So when I write this, I'm actually just saying, well, on the one hand, I'm saying that there is something that's worthy of being called the derivative of f at z0, and that when you put whatever complex number this is here, the remainder term, which you could say is defined to be the left side minus all this other junk, the remainder term then satisfies this property. It goes to 0 in the way that it should. Okay, so that's what we know. All right, let's, okay, so our goal, so this is just setting us up for using the differentiability of f at z0, but our actual goal is to show that this vanishes. So we're trying to show that for suitably chosen n, this becomes very small. Okay, well, let's fix n and then think about how we could analyze this based on this linear approximation for f with remainder going to 0 in the way that it should. So for the moment, fix n. Then the integral of, and let me fill in a dummy variable here, f of zeta d zeta along the nth triangle path, alpha n, is going to be the integral of f of z0 plus f prime of z0, z minus z0, zeta minus z0, rather, plus r of zeta, d zeta. Now, let's focus on this portion here and then this portion. So this first portion actually has an antiderivative that we can write down. It's very simple function of zeta, right? So this portion has antiderivative f of z0 zeta plus 1/2 f prime z0 zeta minus z0 squared. That would be the antiderivative of this, right? So if this has an antiderivative and I take a contour integral along a closed curve, all the triangles are closed curves, they start and end at the same place, then I get 0. So the contour integral of this portion is 0. So that means this is just the contour integral of R only. Okay, so the contour integral of f along alpha n is the contour integral of R. So R is actually all we have to work with. All we need to work with is R. Okay, so maybe I can update that information by just no, maybe I should leave this since this was an arbitrary n. This does work for all n. I can just write R here. Okay, so now we have this. Now this is what I'm trying to show can be made arbitrarily small by suitable choices of n. Okay. And remember, let's also remind ourselves the main fact about R is that this goes to 0 as z goes to z naught. Okay, so what's next? Right, I think we're ready to use this limit fact and try to get this to be smaller than epsilon, where epsilon is arbitrary. So let epsilon be greater than 0. We will show that by a suitable choice of n, this is smaller than epsilon. Then we will be done. So since this goes to 0 as z goes to z naught, there's going to be some delta greater than 0 such that let me do this, let's write it like this. R of z is less than epsilon z minus z naught, with modulus bars here. So originally this inequality would have been this, because I'm getting this delta from the fact that the limit of this function as z goes to z naught is 0. But I have rewritten it like this. Oh, sorry, I have left out also that this happens when z is within delta of z naught and not equal to z naught. Whenever z is, let's say, in the punctured disk of radius delta at z naught. Okay, so that's pretty good. I've got a bound for the integrand in this contour integral. Sometimes I have this bound, actually. I have this bound when I'm guaranteed that the entire triangle, alpha n, the entire triangular path, actually lives inside this punctured disk. The thing is, the triangles are shrinking in size. You could say they're shrinking in diameter. And their length shrinks towards 0. So let's count this as one of those facts that we'll accept for now so we can finish, and then you can verify later if you want. So n, we should be able to choose n, since the triangles are shrinking in size, shrinking towards 0, we should be able to choose n large enough that alpha n, this triangular path, I guess the range of this function, the image of the path, is fully contained in there. Well, actually what you can do for sure is this, where I haven't deleted z naught. But you can also do it deleting z naught, because z naught should not live on the live in the image of any of these paths. If z0 were in the image of one of these paths, then it would get excluded from the next path down, possibly. Is that true? I guess that's not necessarily true. If z0 is on the midpoint of one of the boundary. Okay, let's leave that as a gap also and check later. Can we choose n large enough so that this happens? I find it not perfectly clear that you can get this to be a subset of the punctured disk centered at z0 and not just the unpunctured disk. Okay. So let's say we can make this choice. Then look at this contour integral. We have a bound for the integrand. So what's the bound? Okay, I've got kind of an efficient way to write this prepared. So the integral of r along alpha n is going to be bounded above by the integral along alpha n of the modulus of r. So this is kind of the triangle inequality. Let me write the dummy variable zeta. And since the integrand here is bounded above by epsilon z minus z0, that's due to this. Sorry, zeta minus z0 d zeta. We have this. And let me pull out the epsilon. Okay. Then, okay, so what I really wanted was a constant bound, right? But this is not a constant, it depends on zeta. That's kind of problematic. But if, so if zeta is on the image of this triangular path, then the distance between zeta and z0 we can bound above in a nice way. So what's the biggest it could be? So say you've got your triangular path. And here's z1n, z2n, z3n. And you know zeta is, z0 is somewhere in the triangle. I don't know where. And zeta is somewhere along the boundary of the triangle. What's the biggest zeta could be? Well, all you need to do, I guess, is look at the longest side of the triangle. And that tells you how big zeta could be. So, here's an example. Maybe like this. Here, the yeah, I don't know. I guess in this example, zeta and z0 are in the triangle, zeta along the boundary. The biggest, or you say the diameter of this triangle, is the distance from here to here, the size of the longest side. So this is no bigger than the length of the longest side of the triangle. Okay, so let's say the maximum of z1 minus z2, z2 minus z3, z3 minus z1, which is definitely no bigger than the sum, right, of the sides. Of the side lengths. also known as the length of the of alpha n. Okay, so there's a nice bound on how far away zeta can be from zeta naught. It's no further away than the perimeter, the length of alpha n. So going back up to our integral here, we have this less than or equal to alpha times the length of alpha n, sorry, epsilon times the length of alpha n times the integral of the function 1 along alpha n. Okay, let's continue this. So the length of alpha n, let's look here. This is actually just the length of alpha n again, right? So we just got epsilon, the length of alpha n squared. So that's our bound. Now, we actually know exactly what the length of alpha n is in terms of the length of alpha n minus 1. So let's just think. The length of alpha n plus 1. What is that in relation to the length of alpha n? So no matter which triangle alpha n plus 1 ends up being, no matter which of the smaller triangles it ends up being, the length, the total length, is going to be half of the total length of the large triangle. So this, the length of alpha n, is 1 over 2 to the n times the length of alpha 0. So that's epsilon. So we got epsilon over 4 to the n, the length of alpha 0. Okay, that is awesome, because the length of alpha 0 is just some constant real number. And here we've got alpha over 4 to the n, which is perfect for fighting against that 4 to the n up there. Okay, so wrapping up. We have f is less than or equal to 4 to the n. This is for the specific n that we chose that ensures that the nth triangle is inside the delta disk centered at z naught is, yeah, it doesn't matter if it's less than or equal to 4 to the n, epsilon over 4 to the n, length alpha 0 is epsilon length alpha 0. And epsilon was arbitrary. So for any positive real number epsilon, this is smaller than that. Therefore, this is 0. Therefore, this vanishes. Okay, and that's what we needed. So the theorem is proven. We've proven that if f is analytic is what allowed us R in this limit, and you've got a triangle inside its domain, then the contour integral along the triangular path vanishes. There are a few things you have to accept along the way, so you could just accept them if you want to, or you can ask about them or try to work them out on your own. One is that the triangles are compact. Always. All triangles are compact. Two is that when you have a nested sequence of non-empty compact sets, each one contained in the previous, then there's got to be a point in their intersection. Their intersection cannot be empty. We needed that point because that was the z naught that we worked with here. And I guess you also needed to know that it's possible to pick n large enough to get the nth triangle in this construction to be inside this punctured disk. Okay, so filling in those three gaps, we have the triangle version of the Cauchy integral theorem.